molecular compounds today. Sharing, drawing, that kind of thing. All right, so if you have any questions as we go through, make sure you ask. I know you won't because you're period 1. I get that. But just humor me, okay? Try. You never know. But seriously, this is really, really, really important here today. So good thing you're here, actually, because that's going to help you out significantly. You do have just a couple things to write down here, so I'll let you do that. Molecular compounds, of course. Molecular, when we say molecular, we're talking about sharing covalent bonds that exist between specific pairs of atoms. It's possible to predict the three-dimensional shape of many small molecules, and we're only going to focus on the smaller ones as far as what kind of shapes they have. We're going to talk a little bit about Vesper today, finally. Vesper stands for, and you should know this, the valence shell electron pair repulsion theory. And if you think about what that says, just that word alone, it's pairs of electrons, right? You remember how we drew those? Pairs of electrons that repel, and they're the valence shell electrons, by the way, and they repel each other. Okay, so pairs of electrons will hook up, and they try to take positions as far apart as possible from each other. Repel, okay? Allows the prediction of three-dimensional shapes. That's what it does for us, so make sure you know this entire sentence here. Valence shell electron pair repulsion theory allows us to predict the shapes based on these simple structures here. The theory is based on the electrostatic repulsion of electron pairs that causes them to take positions as far apart as possible. Also, make sure you know that as well. Right? This isn't going to make a lot of sense for you right now. Basically, the LP stands for lone pairs, and BP doesn't stand for Boston Pizza. It stands for bonding pairs. Okay, and I'll show you that a little bit later here, I think. If a molecule has more than one central atom, it's advisable to separate them and predict separate shapes for each part. We're not going to do very complex or very large ones. We're just going to keep it fairly straightforward and simple. So if they do get really large, then you may have to break it into smaller components to name them the shapes, but for the most part it'll be fine. Next part. We use, okay, actually I'm going to do this to you here because you guys get to cheat on me. This is important. We use A to represent a central atom. So we're going to come up with a general formula for these. Okay, A is always going to be the first letter, and it represents the central atom. So for example, if we had some carbons and hydrogens, A would be the carbon. We put the carbon in the middle because it has the most bonding capacity, best bonding capacity, most unpaired electrons, yes. So A represents the central atom. X, so we got A, it's going to look something like this here, A, X, and then sometimes we will need an E, not all the time. Okay. X represents the atoms that are bonded to that central atom, how many there are, all right. And E represents the number of lone pairs on the central atom. So that goes with that, all right. E only, listen, E only refers to A. Lone pairs on the central atom. And even though I just said that nice and slowly, somebody's going to goof that up. Okay? E only applies to A, the central atom. Lone pairs on the central atom. Okay? Now, I think you guys have a little bit of writing to do there. I believe, yes. So, the general formula is usually seen as AX with a little subscript, E with a little subscript, where M is the number of atoms and E is the number of lone pairs. And the best way to do these is just to give you some examples and go through each of the shapes here. So that's what we're going to do here. Next page. Anything that I have on these pages you need to memorize, basically you need to know. Okay? So the first shape we're going to look at is what we call linear. Linear. Linear has a symbol that's AX2, so these all go together. Okay? If it's AX2, it's called linear. If it's linear, it's AX2. If it's AX2, the bond angle is 180 degrees. If it's linear, it's 180 degrees, the bond angle. Right? here's a few examples here. Usually consists of 2 double bonds around a central atom, or a single and a triple. You don't have to remember that, because you're going to draw these and you're going to have to kind of compare them. So you don't have to memorize that part. All right. But let's take a look at a few examples here. When we talk about bond angles, we're talking about the bonds basically around the central atom from one bond to another bond. Okay? So if this is my central atom here, A, whatever that happens to be, the bond angle we were referring to is the bond between here to the next bond. How many degrees is that? And it's 180. In this particular case, linear. Think of a line. Okay? Line, right? So this would be right here, 180 degrees. Straight line all the way across. Okay? Makes sense. It's linear. AX2 goes with that. Those all mean the same thing. Okay? Here's some examples. CO2. Well, we'd start with this, C, right? O looks like this. You guys can write these in, of course. And O looks like that. And when these atoms get close enough together, these are all non-metals, of course. Okay. When these atoms get close enough together, these will hook up here, and these will hook up here to make that molecule. And then, of course, we have some extra stuff to do here yet. So we have this. Right? We've drawn this one before. We have to make sure we have an octet, right? We draw this. So sharing these two here, sharing that one and that one there. Okay? So we can hook these up basically, and we will get something that looks like this as your best diagram here. Okay. CO2. CO2 is what we look at. It looks linear. How do we know for sure? Well, this really looks like this, right? A to the X to an X, like that. Okay. So that's what you're going to do. You're going to draw these out, and you're going to say, what formula does this look like? AX2, etc., etc. So this is what we would call AX2, A1, 2. What you have to keep in mind here is a few things. First of all, because it has double bonds, I do not care. It has nothing to do with this. Okay? You can have triple, it doesn't matter. Okay? So the bonds do not matter. It is A and an X and an atom bonded to the central atom. A turns out to be the central atom here, right? This is your atom. Right? So, AX2. How many lone pairs do I have here on my drawing? And the answer is none, correct? So I do not need an E in this particular example. Is there lone pairs over here? Are those lone pairs there? On O. Are those called lone pairs? Yes. Are they on the central atom? Does not matter then. Okay, don't care. Right? So, has all to do with A, and basically what's hooked to A. Okay? In this case, 2 atoms. Right, let's take a look at the other one here. HCN. I think was it HCN. So H looks like this. A C looks like that. And N looks like that. Okay. So if we're going to hook these together, right? I would take the one that forms the most unpaired electrons, or the best one that you have to get. That one's good. Put an H somewhere wherever you wish. Put it there. And remember, if that's going to be my middle atom, if C is going to be my middle atom, maybe I want to put the N on the other side. Something like this. And we start to need to make a molecule, right? We've done this before. Yes. And we are going to start hooking these up. So I can hook that up, and I can hook that one up there. And then you'll notice that, of course, we don't have an octet, but yet we still can do some sharing here. So it's going to turn out to look something like this here. These two can hook up, and that one can hook up there to give me actually a triple bond in between those. There's the original one there. There's the 2 dots on the bottom. And there's the 2 check marks there. Triple bond, N, and like I said, tries to spread itself out as best as possible. Okay, let me just move that up here for a sec. All right. Once again, okay, this one here, central atom, right? Okay. AX2 again, yes? When you say AX2, you automatically think, what's the name of that shape? Because that's what I'm going to ask you. You're going to say AX2, anything that's AX2 is linear. Okay, so you would write down linear. And then you would also say, of course, what's the bond angle? And you would say 180. All these kind of mean the same thing, really, but they all go together, always. Okay, good? Questions? Okay, next. Trigonal planar is the next one we are going to do. Trigonal planar. Trigonal, when I say the word trigonal, you think what? Trigonal, try. Number 3, right? So trigonal, planar. What does plane mean? We talked about it yesterday, actually, a little bit, but what does plane mean? Flat, right? Flat surface. So that's what we're looking at here. These all are flat quantum. AX3, trigonal planar. That's the formula of the trigonal planar. AX3 is trigonal planar and has the bond angle of 120. And it's called 120 because that's okay, but it's bonding of 120. Okay. Trigonal planar shapes have one central atom with 3 electron groups that lie in a flat plane. All of the electron groups may consist of bonding electrons or electron configuration. We'll talk about that in a sec here. Have your central atom have 3 bonded to it. So it looks like that's an X there. Now it's not always 120, that's the thing. And I'm going to give you some examples here first. First one we're going to do is not BF3. By the way, BF3. I wonder if that stands for best friends forever, forever. They're really good friends. COCl2. Let's do that one first. CO, so there's C. Here's an O. Cl. Okay, and we need 2 of those. So, as always, and we're going to do this again, you're going to get some homework here based on this. You're already you would want to take carbon, both unpaired electrons, with that one in the middle, yes? So we'll take carbon. I have to put 2 Cl's onto here. Cl can only form 1 bond, yes? Because it has 1 unpaired electron. So that looks like a good thing there. Now you might say, why is it one size? Because that felt like it. So maybe it was. Take that. O, you can put on the top of the bottom. Okay? If you're a rebel, you'll put it on the bottom. I am not. I like to follow conformity. So I'll put it on top. I don't know what that means exactly, but whatever. Okay? And we need to hook this together. And yes, you can count up electrons and do it that way as well. You have to be a little bit careful with that. Okay, connection, connection, connection. I have 1 extra one here, and I have 1 extra one here. And those 2 combine together as well, right? They're on different atoms, and they're allowed to be shared. So really what I'm getting here is this. Now, I'm going to tell you, kind of, if I just kind of went ahead with that safe drawing for a while, that's not the best diagram, right? Valence shell electron pair repulsion, Vesper, says the valence shell electrons, the shells that we're pairing and that are being shared here, electrons, they want to pair and repulse each other. So they want to get as far apart from each other as possible. Okay. So how are we going to do that? Well, we're going to put we're going to put our C here. Okay, double bond O, for example. And if I want to try to put them as far apart as possible, I'd probably draw my two CLs down there on a little bit of an angle. Okay. Remember, AX3, the angle's 120. Yes? If I draw it like this, does it look like 120? So we want to try and kind of somewhat represent that here. Remember, everything is as far apart as possible. So we'd probably look at something like this here as the best diagram. Kind of something like that. Alright? Once again, you might say, you know, well, how is this? It's got a double bond in there, etc., right? And once again, I don't care what kind of bonds it has. I'm looking at the central atom and what's bonded to that central atom. That's going to determine the shape. So A, X, X, X. You might say you can't do that. It doesn't matter what's bonded to it. It just matters how many atoms are bonded to it, or how many lone pairs we have. So I know that O and Cl are different. I don't care. It doesn't matter. Okay? They could be all the same. They can be all different. I don't care. Okay? So this is AX3, of course. Yes? AX3. No lone pairs on the central atom. Yes, there's a double bond. I don't care. AX3. Here's the only problem here, okay, with this one. When you look at this actual bond angle here, here, and here, okay? Now, if everything was nicely distributed and nice and even, we would probably say it's 120, 120, and 120. But does this look like it should be symmetrical to you and nice and spread out evenly? What do you think? Keeping in mind that electrons, pairs of electrons repel each other. Do you have more pairs of electrons up here? Yes? No? How many electrons do you have up here? Altogether, being shared there. Not a trick question. How many? Somebody. Say it. 4. Okay? So you get 4 electrons here, but only 2 here and only 2 here. So what actually happens is, because you have more electrons up here than you do with these other bonds here, they're going to basically repel each other more. They're going to push a little bit more because electron pairs repel each other. Well, there's more electrons here, so they push a little bit harder on this bond here, and they push a little bit harder on that bond there, is what actually happens. If they were all single bonds, I would say, oh, it's only 120, 120, 120. But they're not. So in this case here, I'd say that this is probably, actually it is, not probably, it's 121 or this one's 121. Because those two are kind of the same bond, so you can write on each side. This one shrinks a little bit, 180. So that's the only one exception they kind of have for that. Okay. 121, 121, and 120. Now, if you said 120, I'm probably not going to mark it wrong, but technically this is a better drawing. Okay, it's the proper angles for that. 121, 121, and 120. For that one. So you can see it's very close to 120, but there is more electrons there, so they are going to push harder. They're going to repel from those from that bond there harder. Right? The next one we have to do is we have to make Vesper and forever here. Now, Unfortunately, BF3, we go to draw B, so B looks like this. We've got 3. We've never drawn B before, have we? There's actually kind of a reason for that. So, which one do you want to put in the middle? What do you think? B or F? Okay, wrong period to ask. B or F? Yeah. Okay. I'm actually going to do this here. I'm going to put an F here. Right? Do I have enough there? Let's try that again here. We'll just do this for now. Okay. So B has 3 unpaired electrons. Each F that we have there happens to match up with that nicely. We could even draw lines here, like so. Okay. And that's probably not the best drawing. We may want to spread it out a little. Good? What do you think? Yeah? Good? Yes? No? What's wrong? Anything wrong, or are we good? What's wrong? Yep. That's right. B doesn't have an octet, yeah? So did we draw it like this? Yeah, we do. That's why I haven't done it before. B, boron, is an exception, okay? It's one of the exceptions to the octet rule. So hydrogen only needs 2. Helium needs 2. Boron can get away with 3 around it, okay? It is an exception. So in fact, when you get boron type of molecules like boron trifluoride, boron trihydride, those are the only ones, okay, and make sure you guys know, these are the only ones that actually form a perfect 120, 120, and 120, okay? And there's different reasons for that, why boron gets away with only 6. We're not going to get into that, all right? So you just have to know that there's always obviously exceptions to the rule. Boron happens to be one of those exceptions. There is no other tricky one. So, but that is an acceptable drawing. That one, if you notice, is all spread out nice and evenly. Yes, it doesn't have 8. I know people are starting to freak out here, but it's fine. But that's the one that's probably a perfect 120, 120, 120. In most cases, you're going to get something that looks like this here, where it's not exactly all spread out. Okay, so the 121, 121, 118. These are both AX3s. These are both trigonal pyramidal, and they both have bond angles of about 120. Okay, that one's perfectly 120. This one here is a little bit off, of course, because of that double bond. All right. So, good. Next one. This one's a little bit of an adaptation to the last one we did. This one's also called trigonal planar, but this one is called bent. All right. And trigonal planar has a formula of AX2E, AX2E. Okay. Bond angle is 120 still, although probably not quite, but that's fine. And we're going to talk about SO2 as a good one for this one. SO2. If you remember, we tried to draw SO2 before. You remember that? I'll draw you a quick one here. Don't draw this. Does this look familiar? Yes? So what's the best way to draw this one? like that, or in this particular case, actually, by the way, AX2E ones, when they don't work out very well, it's probably AX2E. It's usually the case. What's the best way to draw this one? Probably counting up electrons, yes? Okay, so we have what? 6 here and 12 for a total of 18. And we would start with, once again, okay, does it really matter which one? You try to make them symmetrical, okay? Ultimately, it's not going to matter, but S, O, and O we'll start with, like we did before. 18 electrons. 1, 2, 3, 4. We start on the outside atoms first, so 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I used up all those. 17, 18. Okay. And of course we stop and say, you know, it's not boron, so we're okay, but does it have an, you know, sulfur and oxygen need to have 8? They're not exceptions to the rule. Does sulfur have 8? And the answer is no. So we would take a pair and we would move it into here. So I'm just going to redraw that just to take our time here with the drawing. So you'd get something like that. Yes? And then some of you would want to put in some lines here instead, and that's fine. So you would say maybe it looks a little bit more like that. Okay, and that's fine too. Same thing. Is that the best diagram we can have? Is everything as far apart as possible from each other? And the answer is no. So we need to kind of take that into consideration. So S has a lone pair. Okay, a lone pair at the top. And that's kind of occupying one of the spots. All right? So since this lone pair is up here, we still need to make sure that we are far enough away from that lone pair, because pairs of electrons repel each other. That pair of electrons is on the central atom. So we need to make sure we spread everything else out as well. So we put our O down here, and then our best diagram would look something like that there. Okay. Remember, okay, this one has a lone pair on the central atom. This is A. There's your E right there. Okay? And this is your X, and this is your X down here. Yes? That is how you come up with the formula AX2. It always goes in this order. AX. We got 2 atoms bonded to the central one, and we have a lone pair on the central one, E. That's your E right there. Okay? So that is how you get that formula there, AX2E. Okay? This one is called trigonal pyramidal. Why is it called, or trigonal planar, sorry, trigonal planar. Why is it called trigonal planar? Why do you think it's still called trigonal planar? What, the last one had how many things around the central atom? What does trigonal planar have around? How many? 5. Seriously? 3, right? 3 things around the central atom, right? Look, BF3, COCl2, right? Look at the drawings. 3 things around it. That's trigonal planar. This is also trigonal planar. There is 3 things around the central atom, so it has the same name. 1, 2, 3 things around the central atom. It turns out that one of those things happens to be a lone pair, though, instead of an actual atom. So we gave it a slightly different name, which is called trigonal planar bent. Okay? Trigonal planar bent. So the bond angle here is still 120. Where is the bond angle on this particular molecule? And that's important to know. Well, as the name implies, it's the angle between the bonds. So the only bond angle we have is right here for this particular one. They say that that's 120. I kind of doubt that, but that's probably on average that's what. Okay. This is not a bond angle because it's not between two bonds, and neither is this, of course. So in this particular one, we only have one bond angle that we can look at. It's 120. So trigonal planar, generally speaking, any type of AX or AX3 has a bond angle of 120, okay, roughly. Unless it be 121. Very close. Next one. Last kind of tetrahedral. Tetrahedral, AX4. Tetra means what? Tetra. 4. So 4 things around the central atom, yes? Okay. Bond angle is 109.5. Here's where we get into more complex a little bit. Not more complex, but just what you have to think of. Tetrahedral are 3-dimensional. So when we draw tetrahedral, we don't draw 3-dimensional. We draw 2-dimensional. You need to analyze the perspective until you can see that in this image here, lines going upward or the plane of the page, the lower line is the right, blah, blah, blah. So when you look at this diagram here, you can kind of pretend, this is probably your best diagram here. This is actually what it would look like here. It is kind of, obviously it's 3-dimensional. You can think of a triangular base here kind of thing. So these 3 here sitting flat, and this one's sticking up. Okay. I'll show you the model here. And we'll do that. The bond angle here is 109.5. 109.5. When we draw them, it doesn't look like that. So we just have to keep that in mind. CF4 and CH4 are 2 examples. Very simple ones. CF4. I don't know if I'm recording the whole thing. So we would draw CF4 like that. This is what we would call the tetrahedral. This, of course, is A, X, X, X. Remember, the X's don't have to be the same, so we could have CF2. I don't care what atoms are bonded to the central one. I just need to know how many times it's bonded. Remember, the feature, what tells you what gauge you're going to have, really this here. It's going to tell you in a certain the A. So AX4, CH4, I don't know, once again, here you go. There's A, X, okay? That one's called tetrahedral. It looks like 90, but it's not, right? It's 109.5. It's 3-dimensional. You're drawing 2-dimensional. So keep that in mind. Other than that, I don't think I need to tell you anything else. Tetrahedral is what that one is called. This one here, the next one we're going to look at belongs, okay, to the tetrahedral family. What does that mean? There's 4 things around the central atom again. But more specifically, we call this one trigonal pyramidal. Trigonal pyramidal. Trigonal implies 3 things and a pyramid kind of thing. So 3-dimensional shape. The formula is AX3, so that's where your trigonal part comes in. Okay. The bond angle is 107.3, and here's a few examples we'll look at. So NH3. I'm not going to spend as much time on this one, guys. Right? NH3 looks like that to start off with. You got an N with 5 valence electrons, 3 unpaired. Each H matches up with that, yes. Okay. You're going to connect them together. So when you draw an H3, you can draw it like that. That's fine. Okay. NH3 would look like that. Once again, this is A, X, X, X. Okay? There is 4 things around here, the central atom. That's why it belongs to the tetrahedral. However, only 3 of those things are atom. That's why instead of saying tetrahedral for this one, you can't call it the same thing. You have to call it trigonal. You can't call it the same thing for 2 reasons. Okay? One, this one has a lone pair on it, and the bond angle here is 107.3. It's not the same bond angle as the last one had. Okay? And there's other reasons as well. We can't call these the same thing, but we'll wait for a little bit for that. Okay? Arsenic trifluoride, same thing. Remember, arsenic, actually you guys did a good job of this last day. You have to remember that arsenic is the same as nitrogen and phosphorus, right? Same group, so it would look like that as well. AX3 with an E, a lone pair on the central atom. Okay? That's your E there, of course. Same, basically the same drawing. Okay? And there's one last one here. AX2E2. And this one is called tetrahedral bent. Okay? Tetrahedral bent. Now remember, we have 2 bent names already. We have trigonal planar bent, and this one is tetrahedral bent. So make sure you distinguish between those. Just don't put down bent, because I won't know which one you're talking about. Once again, AX2E2 means it's tetrahedral bent. Bond angle is 104.5 for this one. Some examples of AX2E2. Well, probably your most bend-shaped, etc., etc. Here's a 3-dimensional drawing of kind of what it would look like. So you'd have some lone pairs, and then 2 atoms bonded to that, basically. Right? A couple examples. Well, very, very famous one. Water is an example of tetrahedral bent. Okay? So we would, of course, hook these up here. Hook these up. And we would have A, X, and X. And that would be an E, and that would be an E as well. So you get their E2 there, basically. Yes? Okay? So A, 2 X's, 2 atoms are bonded to A, and 2 lone pairs are on A. The bond angle we're talking about here, right in here, is the only bond angle, by the way. Again, it's 104.5 degrees. So it's a little bit smaller. And last one here, S. Looks like that, H2S. All right. Once again, A, 2 atoms bonded, 2 lone pairs. AX2E2. All right. AX2E2. Once again, bond angle is 104.5. Now, one last, well, you got some other stuff here. You got this little chart for you here that I made for you, but listen, okay, some of this stuff is probably a little bit extra. As far as the shape goes here, they just kind of give you an idea of what the shape would look like. I wouldn't focus too much on that shape, all right? You got AX2 is linear. This means that they're all bonding pairs. So when we say bonding pairs, we mean that there's going to be atoms bonded to the central atom. That's what that means. So AX2, remember back to CO2? There was two oxygens bonded to carbon, so that's a bonding pair. Okay, all bonding pairs. AX3, right? Our examples for AX3 are BF3 and CH2O, all bonded. Okay. This is AX2E. When you see that, of course, you have to know that there is 2 bonding pairs and a lone pair, right? Think back to SO2 if you want. They give you some examples of each one as well, right? Et cetera, et cetera. Now, this is a really good study sheet for you guys. It's only missing one thing that I'd ask you to make sure you guys know, which is, of course, bond angles, yes? So what I would do is I would take about 5 minutes today and sometime and write down the bond angles along this side here. And don't do it right now because I got a little bit extra stuff for you to do right now. I would put down the bond angles along the side, and this is a great study sheet for you guys. Okay? It's not very clear, and I apologize for that, but that's just how it came out. How do you predict these molecular shapes? Well, you have to be able to draw them first. Okay? So you draw your Lewis structure. Basically, you have to decide what it's going to look like. So it's going to be practice with drawing molecular compounds today. You may take a little bit of time. You might have to, really think about that. Determine how many atoms are bonded to the central one, and what's bonded to the central atom. Is it just atoms, or are there lone pairs as well? Right. So that's going to all take place here. You guys got some homework here, for example. But before that, actually, you got to do that thing. I'm just going to show you one quick, write this down somewhere so you guys make sure you know. I'll just give you oops. Here's 3 molecules that I put up here. CH4, NH3, and H2O. What do these molecules have in common? What do they have in common? Yep. They do. Looking at, you're right, and I kind of picked that for a reason, because I wanted you to just kind of look at those. But as far as structures go, if you look at the central atom, what's in common with these states, with these 3 molecules? How many things are around the central atom for each one of these? How many? Somebody. Anyone? 4. Yes? Okay. This one, of course, is AX4. Yes? AX4. Yes? AXXXX. AX4. This one is AX1, 2, 3. Yes? And it's E. So is there 4 things around the central atom there? Yes. This one, A, look guys, 1, 2 atoms. 1, 2, lone pair. Tetrahedral. Part of the tetrahedral family, 4 things. Trigonal pyramidal is called. Tetrahedral bent. Yes? Are the names. Okay. Good so far? Why didn't we just, if there's 4 things around them, why don't we just call them all tetrahedral? And the answer is, well, this is 109.5. This is 107.3. And this is 104.5. Why the difference? If they're all tetrahedral, if they all have 4 things, why is there a difference in bond angle? Anybody want to venture a guess? No? Because you're period 1? The reason is actually up here. This one here, everything's spread out as far apart as possible from each other. AX4. This is 109, that's 109.5, that's 109.5, that's 109.5. It's 100% symmetrical, okay, all the way around. This one is 107.3, 107.3. But remember, that's just the bond angle here. You got this lone pair up here. So if everything was completely symmetrical, then this right here should have been 109.5, yes? Same as the last one. But it's not. And that's because lone pairs repel more than bonding pairs. So what actually happens here is you get a structure that kind of looks like this. Alright? So as far as NH3 goes, it actually looks more like that. Because lone pairs have a greater repulsion than a bonding pair to a bonding pair. So what happens is this lone pair here pushes more and pushes more, repels, pushes away, right? So if you're like this, and the lone pair is here, and if I'm going to push more, what has to happen? These have to go down. As a result, when these go down, what happens to the bond angle? It shrinks. Where else is it going to go? Right? So now, what's happened is this is shrunk down to 107.3. Right? It was 109.5. Everything was nice and spread out. But now you put a lone pair up here and it pushes more. Well, this has to shrink. It pushes away. When that happens, it shrinks this angle. Alright? So that's 107.3. That's why we didn't just call them all tetrahedral. They're not all the same shapes. They're slightly different. Guess what? Two lone pairs. By the way, you quite often see water drawn like this. Okay? So water has two lone pairs. The repulsive force is even greater from those two lone pairs. They push even. That's supposed to be a fat arrow. They push even more on those bonds. And once again, what's the option? When you have two lone pairs pushing more, right? It's got to shrink everything else down because there's less room for everything else to go. So that's why that shrinks down to 104.5. And you should know that. Okay, that's important. Lone pairs repel more. Okay? The more lone pairs you have, the more repulsion you have. All right? Now, if you look, we're just focusing on the central atom again. So that's all we're talking about here. Once again, if there's lone pairs out here, that's something different. We'll talk about that some other day. That does affect some parts of the molecule, but we're not going to worry about that today. Okay? So, everything's spread out nicely in this first one. Shrinks a little bit due to the lone pair. Shrinks more due to two lone pairs. Okay? So that's why different angles for each one of them. Tetrahedral, trigonal pyramidal, tetrahedral. Okay? Just going back here for a sec, just a little reminder. So, there's only one with two things around it. It's AX2. So there's only one linear structure, AX2. That is it. After AX2, we go to AX3. AX3 or AX2P. So there's one that has AX2. There's two structures that have three things around it. Two structures that have three things around it. And when we get to tetrahedral, when we get to the 4, there's three different structures you can have. Okay, which we've drawn there. Alright? So here's what you're going to do today. You guys got some other homework there too. You're going to draw these out. Okay? So you're going to do I think it tells you up here. Hopefully. Anyway, maybe not. Did I put it here? Okay, I guess not. So, I guess we have to write this down. You're going to draw these out first. So, step 1, obviously draw. You're then going to tell me the general formula for that. Right? So, formula. In terms of AXE kind of thing. And you may not need AXE. So, formula. And you're going to tell me the name of shape. Shape. So trigonal pyramidal, tetrahedral, tetrahedral bent, whatever. Okay. Trigonal planar bent, and the bond end for each one of these. Alright. And that's all I got for you today here.